Good day. We carry on with Ka Intro. This should be the second video, and we are looking at the third page. We'll start with B. So, this example, we start with a weak acid. We're looking for the pH. We're given the starting moles and volume, which means the starting concentration of acetic acid. And we're going to proceed. We start by writing out the equation, and we set up our ice chart. So we have our 0.25. The x value is so small, we can say it's still 0.25, and we end up with x and x. Of this, what are we really after? Well, it says we want the pH, and what that means, we really want to get the H3O+, because we have the H3O+ concentration. It's a very quick flip to get a pH. There's our Ka expression. We're going to know the Ka. We're going to look that up on the chart. We're going to know this concentration, that's 0.25, and we're solving for the x. We see these two values are the same, so this is going to be an x squared. Well, you can see my square root symbol didn't go very well. I've rearranged and I'm solving for the H3O+. The Ka is 1.8 times 10 to the minus 5. I looked that up on the Ka chart. I multiply by the 0.25 and I take the square root of that mess. Once I have the square root, I find it 0.0021 molar, and I minus log it, and I get 2.67. Remember, this has two sig figs because the numbers to the right decimal point are significant digits. This had two sig figs, and this represents our power of 10. C is going to be a slightly different question. In fact, it has two questions. In this case, we don't have to find the pH, we're given it. Like before, we have a starting concentration. So first we're going to find the Ka, and then we're going to show you how to determine a percent reaction because many textbook questions will ask you about percent reactions. And if you look at the textbook Ka chart, it actually gives you the percent reaction for many of the weak acids. So we need our equilibrium reaction. There's a carbonic acid becoming bicarbonate to produce an acidic solution, but not completely. That's why it's ice. It's an equilibrium. And you're saying, how did I get this 0.0032? Well, the question gave me the pH. So if I make that minus 3.49, anti-log it, that's how I got this number. So when given a pH, you can get to your actual H3O+. And I know that's also going to equal the bicarbonate concentration. There's my Ka expression, so I now have all the information I need. 0.00032 in there, in here, and the 0.24 goes right there. Now let the calculator do the work, and the Ka comes out to 4.3 times 10 to the minus 7. Now you say, what do I do about the percent reaction? Well, what that's saying is, hey, let's compare what we started with to how much reacted. And this is a one-to-one deal. So this is how much reacted versus the starting concentration. So we're going to take the H3O+ concentration, divide it by H2CO3's concentration, and make it a percent. So here's our percent reaction. Boom, boom, boom. Anytime we make something percent, just multiply by 100%. There are the numbers we grab from our chart, and we see it's tiny, 0.13%. So that means if we had it means if we had 1,000 molecules of H2CO3, only 13 would actually have reacted or ionized. So that's a pretty low percent, and that's why it is considered to be a weak acid. So that was, I believe, video 2. So video 3 will be coming up, and it will carry on with all kinds of weird and wonderful things. I think one more example like this, and then we'll get to the basis.